Now in this lecture I will answer two questions. In the first question, we find out the size of this angle APC is equal to x. So we have to find out the value of this angle x. In the second question, we find out the length of this line 7 CD is equal to x. So we have to find out the length of line 7x equals to CD. So we start with the first question. In the drawing, we have triangle ABC. This is angle ABC, equals to 15 degrees inside. This is angle ACB, equals to 30 degrees inside. We also know that BP equals to PC. Again, our test is to find out the size of this angle APC equals to x. So we have to find out the value of this angle x. So first of all, we know that BP equals to PC. So if we define the length of line 7 BP as A, then PC must be also equal to A because they are equal to each other according to what is given us a question. So BP equals to A, units in its length, and therefore PC must be also equal to units in its length because they are equal to each other. In the next step, we will do a construction. That is to say, we will extend side CA of this triangle ABC. We will extend side CA by a straight line. And we create angle of 15 degrees at point B. But again, next step, we create angle of 15 degrees at this point B. So one leg of the angle that is equal to 15 degrees inside will be the leg BA, and the second leg will be a leg that creates 15 degrees with the leg BA. And again, the red line, this is the second leg of this angle, creates 90 degrees with the leg BA. So this angle equals to 15 degrees inside according to our construction. In the next step, we'll extend this leg, the red leg, by a straight line until it touches the extended side CA. And we will define the touching point of the extended red leg with the extended side CA. This point is point M. By doing this construction, we created this triangle BMC. This triangle BMC, those two angles are both equal to 30 degrees in their sizes, and therefore triangle BMC is an associated triangle. So if you write it down, triangle BMC is an associated triangle because of the fact that those triangles are both equal to 30 degrees in their sizes. the big triangle, triangle BMC, is an isosceles triangle. The base of this isosceles triangle, triangle BMC is BC. So here you can implement rule 20 in our drawing. Repeat quickly rule 20. According to rule 20, the perpendicular to the base of an isosceles triangle bisect the base. In the drawing, we have triangle ABC, that is an isosceles triangle. The base of triangle BC is BC, of course. According to this rule 20, the perpendicular to the base of an isosceles triangle bisect the base. So from point A, we go perpendicular AD on the base BC. So this angle equals to 90 degrees, and this angle also equals to 90 degrees in its size according to our construction. And according to this rule 20, the perpendicular from the vertex A to the base BC, that is to say, the perpendicular AD bisects the base BC. That is to say, it divides the base BC into two halves. The first half is BD, and of course equals to the second half DC, and each half must be equal to BC over 2. So BD equals to DC equals to BC over 2. So we can implement rule 20 in our drawing. In our drawing, we have, this is the isosceles triangle BMC. According to rule 20, and BC is the base of this isosceles triangle BMC. According to rule 20, the perpendicular from point M to the base BC bisects the base BC. That is to say, it divides the base BC into two halves. And therefore, the perpendicular from point M to the base BC must touch the base BC at point P and not in any other point. Why? Because of the fact that point P is the midpoint of BC. Why point P is the midpoint of BC? Because at point P, BC is being bisected into two halves. The first half is A, the second half is also A. Therefore, the perpendicular from point M to the base BC must touch the base BC at point P and not in any other point. So actually, MP is the perpendicular. MP is the perpendicular. Therefore, this angle equals to 90 degrees. And this angle also equals to 90 degrees according to our construction. Okay. So in the next step, we will focus on this right triangle MPC. The right triangle MPC sinus 30 degrees equals to MP over MC. Again, sinus 30 degrees equals to MP over MC. So write it down. The right triangle MPC actually we choose this triangle BMP, the right triangle BMP, sinus 40 degrees equals to MP, sinus 40 degrees equals to MP over MB. Write it down. The right triangle BMP it's very easy to see that sinus 30 degrees equals to MP over MB. We define the hypotenuse of this triangle BMP BM as 2B. The hypotenuse MB equals to 2 units in Islam according to our definition. So if you found out that sin square is equals to MP over MB. MB is 2B, therefore MB by 2B. So it is MP over MB is 2B according to our definition. Sin square is 1/2. So sin square is by 1/2. So 1/2 equals to MP over 2B. Here we multiply this equation by 2B, and we get that 2B over 2 equals to MP. Here we have 2 on both sides of this equation, so 2 will get cancelled. And finally we found out that MP equals to B units in Islam. The perpendicular MP equals to B units in Islam. This is the perpendicular MP, it equals to B units in Islam. This is line segment AB. Line segment AB bisect angle MBC in the big triangle MBC. Again, in the big triangle MBC, line segment AB bisect angle MBC. Divides angle MBC into 2 halves. Each half equals to 15 degrees in size. Therefore, AB is the angle bisector of triangle MBC. Again, AB is the angle bisector of this big triangle MBC. So until now, we have known that AB, this is line segment AB. Line segment AB is angle bisector of the big triangle MBC. And because of the fact that line segment AB is the bisector of triangle MBC, angle bisector of triangle MBC, we can implement here the angle bisector theorem. According to angle bisector theorem, so repeat the question on angle bisector theorem. This is actually rule 19. So according to angle bisector theorem, if AD is angle bisector of triangle ABC, again AD, the red line AD is angle bisector of triangle ABC. Why AD is angle bisector of triangle ABC? Because of the fact that AD bisects angle BAC into 2 halves. Each half equals to theta. So if AD is angle bisector of triangle ABC, then AD divides the size of this triangle ABC proportionally. Again, if AD is angle bisector of triangle ABC, then AD divides the size of triangle ABC proportionally. That is to say, BD over DC equals to AB over AC. And again, if AD is angle bisector of triangle ABC, then angle bisector AD divides the size of triangle ABC proportionally. That is to say, BD over DC equals to BA over AB. Again, BD over DC equals to BA over AC. So actually, angle bisector theorem has 2 directions. If you know that AD is angle bisector, then AD divides triangle ABC proportionally. That is to say, BD over DC equals to BA over AC. The other direction of angle bisector theorem says that if we know that BD over DC equals to BA over AC, that is to say, line segment AD bisect triangle ABC proportionally. That is to say, line segment AD bisect triangle ABC in such a way that BD over DC equals to BA over AC, then line segment AD is angle bisector of triangle ABC. And again, angle bisector theorem has two directions. So we use the first direction of the angle bisector theorem. The first direction of angle bisector theorem says that if AD is angle bisector of this line ABC, then angle bisector AD divides line ABC proportionally. That is to say, BD over DC equals to BA over AC. So we implement angle bisector theorem, Rule 19, in our triangle, the big triangle, triangle MBC. And again, we know that AB is the angle bisector of this triangle, the big triangle, triangle BMC. And therefore, according to angle bisector theorem, angle bisector AB bisect the sides of the big triangle BMC proportionally. That is to say, BP over PC equals to BA. That is to say, MC MB over BC equals to MA over AC. Again, angle bisector AB divides the sides of the big triangle BMC proportionally. That is to say, BM over BC equals to MA over AC. Okay, so now, angle bisector AB divides the big triangle BMC proportionally. That is to say, MB, according to Rule 19, MB over BC equals to MA over AC. This is according to Rule 19, that is the first direction of angle bisector theorem. MB is 2B over BC. BC in total equals to A plus A, that is 2A. BC is 2A. So 2B over 2A equals to MA over AC. We have 2 in the denominator, so 2 will get cancelled. And finally found out that B over A equals to MA over AC. So B over A equals to MA over AC. So in the next step we'll focus on this right triangle MPC. In this right triangle MPC, line segment AP bisect triangle MPC proportionally. That is to say, B over A equals to MA over AC. So this is the opposite. Then converse. The converse of angle bisector, the converse theorem of angle bisector theorem. Why? Because we know that in the right triangle MPC, line segment AP bisect actually divides the sides of this right triangle MPC proportionally. That is to say, B over A equals to MA over AC. And because of the fact that line segment AP divides the sides of this right triangle MPC proportionally, line segment AP must be angle bisector of triangle MPC. This is the converse theorem of angle bisector theorem. We know that line segment AB bisect the sides of this triangle MPC proportionally. That is to say, B over A equals to MA over AC, and therefore line segment AP must be angle bisector of this right triangle MPC according to rule 21. So if we click on rule 21, according to rule 21, if we know that this is line 7 AD, we know that line 7 AD bisects, line 7 AD divides the size of this triangle ABC proportionally. That is to say, BD over DC equals to BA over AC. Again, we know that BD over DC equals to BA over AC. Therefore, line 7 AD must be angle bisector of triangle ABC. This is the converse theorem of angle bisector theorem. So, as I mentioned before, angle bisector theorem has two directions. So, this is the converse theorem of angle bisector theorem. We know that BD over DC equals to BA over AC. Therefore, line 7 AD must be angle bisector of this triangle ABC. So, actually, we only implemented the angle bisector theorem on this right triangle MPC. So, as I mentioned before, we know that B over A equals to MA over AC. So, line 7 AP divides the size of this triangle MPC proportionally. Therefore, line 7 AP must be angle bisector of the right triangle MPC according to rule 21. So, until now, so in this right triangle MPC, we have line 7 AP divides the sides of this right triangle MPC proportionally. That is to say, B over A equals to MA over AC. And therefore, line 7 AP must be the angle bisector of this triangle MPC. So we have that from the fact that line 7 AP divides the size of this right triangle MPA proportionally, that line 7 AP is the angle bisector of this right triangle MPC. So line 7 AP is the angle bisector of this right triangle MPC. That is to say, angle bisector AP divides angle MPC into two halves. So, angle bisector AP divides angle MPC into two halves. But because of the fact that angle MPC equals to 90 degrees in size, each half must be equal to 45 degrees in its size. The first half, MPA, equals to 45 degrees in size. And the second half is angle X, that is also must be equal to 45 degrees in size. We actually found out that the angle that we are looking for this question, that is angle X, is equal to 45 degrees in size. And now we actually found out that this is angle APC. Angle APC equals to angle x, and angle x equals to 45 degrees in size. So the answer to the first question, that the missing angle x is equal to angle APC is equal to 45 degrees in size. So we finish with the first question. In the next step, I present you the second question of this lecture. And answer on the second question. In the second question, our task is to find out the length of this line segment CD is equals to x. So we have to find out the length of line segment x is equals to CD. So in the moment we have a semicircle. We know that this is line segment OE, it is equals to 5 units in itself. This is line segment EB, it is equals to 4 units in itself. Likewise, PQ equals to CQ equals to QE. So all those three sides are equal to each other in their lengths. So if we define the length of side PQ as A, then side line segment CQ must be also equal to A, and line segment QE must be also equal to A, because of the fact that all those three line segments are equal to each other in their lengths. So each of them equals to A units in its length. So in the next step, we will join points C and P together by straight line. By joining points C and P, we get the right triangle PQC. In the right triangle PQC, those two sides are equal to each other. Each side is equal to A. And we have the rule that in front of equal sides in the triangle, there are equal angles. So in front of those two equal sides in the right triangle PQC, we have those two angles that must be also equal to each other in the sizes. So if we define the size of this angle as alpha, then the size of this angle must be also equal to alpha, but they are equal to each other according to the rule that I mentioned. In the right triangle CPQ, the sum of the angles must be equal to 180 degrees according to the rule that says that the sum. This right triangle CPQ, the sum of the angles must be equal to 180 degrees, according to the rule that says that the sum of the angles in any triangle is equal to 180 degrees. That is to say, alpha plus alpha is 2 alpha plus 9 degrees, and that must be equal to 180 degrees. So in the right triangle CPQ, the sum of the angles must be equal to 180 degrees. That is to say, 2 alpha plus this angle, this is the right angle, total must be equal to 180 degrees according to the rule that I mentioned. So in total, if you round down that the right triangle CPQ, 2 alpha plus 9 degrees equals to 180 degrees. Here we subtract 90 degrees from this equation, and we get that 2 alpha equals to 180 degrees minus 90 degrees is 90 degrees. Here we divide this equation by 2, and finally get that the missing angle alpha equals to 90 degrees over 2 is 45 degrees. Both those two angles equal to alpha, therefore each angle equals to 45 degrees in size. So if you now in the next step, we'll join points Q and E together by straight line. Those two. We'll join points P and E together by straight line. By joining points P and E, we created the right triangle. We created triangle PQE. This is triangle PQE. It's given us a question that CE is a straight line. So if we focus on the upper side of this straight line CE at point Q, here the sum of the areas must be equal to 180 degrees according to rule 3. Rule 3 says that the sum of the areas on one side of a straight line is equal to 180 degrees. So which angles we have at the upper side of the straight line CE at point Q? We have this angle, that is the right angle, plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees and inside. And therefore, triangle PQE is a right triangle. So repeat on the same process that we have done in this right triangle. Very quickly. This right triangle PQE, in front of those two equal sides, we have those two angles that must be also equal to each other and their sizes. If we define the size of this angle as alpha, then the size of this angle must be also equal to alpha. So we already found out that in this right triangle PQE, those two angles are equal to 45 degrees in their sizes. So therefore, those two angles must be also equal to 45 degrees in their sizes. It's exactly for the same reason that those two angles must be also equal to 45 degrees in sizes. So the big angle CPE equals to 45 degrees plus 45 degrees, that is 90 degrees. It is a right angle. In the next step, we will complete this semicircle to a circle. So we completed the semicircle to a circle, and we'll extend side PE by side line until it touches the circle. And we will define the touching point of the extended side PE with this circle. This point is point N. Likewise, we will extend this side CE by side line until it touches the circle. And we will define the touching point of this side CE with this circle. This point is point M. In the next step, we will join point C and N together by side line. This is peripheral CPN. Peripheral CPN equals to 90 degrees in size. And peripheral CPN subtend on chord CN. Again, peripheral CPN is equals to 90 degrees in size, subtend on this chord CN. And therefore, according to rule 5, peripheral CPN must be equal to peripheral, and therefore, according to rule 5, chord CN must be the diameter of this circle. So repeat quickly on rule 5. according to rule 5, any peripheral angle that is equal to 90 degrees in size must subtend on the diameter of the circle. In the drawing, we have a circle. This is peripheral angle MAN. Is equal to 90 degrees in size, and therefore, according to this rule 5, peripheral angle MAN must subtend on the diameter of this circle. Peripheral angle MAN subtend on chord MN, and indeed chord MN is the diameter of this circle. So according to rule 5, any peripheral angle that is equal to 90 degrees in size must subtend on the diameter of the circle. So as we mentioned before, we can definitely implement rule 5 in our drawing. Why? Because in our drawing, this is peripheral angle CPN that is equal to 90 degrees in size. Therefore, peripheral angle CPN must subtend on the diameter of the circle. Actually, peripheral angle CPN subtend on chord CN, and therefore, according to rule 5, chord CN must be the diameter of this circle. Okay, now, this is chord CN, that is the diameter of this circle according to rule 5. Actually, rule 5 has two directions. The first direction of rule 5 says that if a peripheral angle equals to 90 degrees inside, then it must subtend on the diameter of the circle. Mn is the diameter of the circle. The converse rule of rule 5 is that if peripheral angle subtend rule 7 says that if a peripheral angle subtend on the diameter of the circle, then it is equal to 90 degrees in size. In the drawing, we have peripheral angle ACB that subtend on chord AB, that is the diameter of the circle, and therefore peripheral angle ACB must be equal to 90 degrees in size. So, rule 5 has two directions. So, in the next step, we join points M and N together by straight line. By joining points M and N, we get that this is peripheral angle CMN. This is peripheral angle CMN. Peripheral angle CMN subtend on chord CN again. Peripheral angle CMN subtend on chord CN, that is the diameter of this circle, and therefore according to rule 7, that is the opposite, the converse rule of rule 5, because of the fact that peripheral angle CMN subtend on the diameter of the circle, peripheral angle CMN must be equal to 90 degrees in size. So, those two angles are defined as vertex angles, and we know that vertex angles are equal to each other. But this angle equals to 45 degrees, and therefore this angle must be also equal to 45 degrees in size, according to the rule that vertex angles are equal to each other. So in this small right triangle EMN, this angle equals to 45 degrees. This is the right angle, therefore this first angle must be also equal to 45 degrees in size, according to all the set that the sum of the angles in any triangle is equal to 180 degrees. So this first angle must be equal to 45 degrees in size. So this small right triangle EMN, in front of those two equal angles, we have those two sides that must be also equal to each other in their lengths. According to the rule that in front of equal angles in the triangle are equal sides that must be also equal to each other in their lengths. Again, according to the rule that in front of equal angles in the triangle there are equal sides. So in front of those two equal angles we have those two sides that must be also equal to each other in their lengths. That is to say, EM must be equal to MN. So if you define the length of EM as B, then the length of ML must be also equal to B according to the rule that I mentioned. So, what is the radius of this circle? The center of this circle is at point O. Point B is the point of the circle itself, therefore OB is the radius of this circle. OB equals to OE, that is 5, plus EB, that is 4. So in total, the radius OB equals to 5 plus 4, that is 9. So the radius of this circle equals to 9 units in its length. So it is now the radius of the circle equals to 9 units. ON is the radius of this circle, because it starts from point O and ends at point N, that is the point of the circle itself. Therefore, ON is the radius of this circle, equals to 9 units in its length. Likewise, OC is also the radius of this circle, therefore it is equal to 9 units. What is the area of this triangle? Triangle COE. The green triangle COE. And again, what is the area of this green triangle? Triangle COE. We know that the area of any triangle equals to the base of the triangle times the height over 2. Because again, the area of any triangle equals to the base of the triangle times the height over 2. So the area of this green triangle COE equals to the base of the triangle times the height over 2. We choose the base of this green triangle COE as OE. The base is OE. The height to the base must create 90 degrees with the base OE. So the height to the base must create 90 degrees with the base OE. Or the height to the extended base OE must create 90 degrees with the base. The extended 90 degrees OE is ED, and CD creates 90 degrees with the extended 90 degrees OE. Creates 90 degrees with the extended 90 degrees ED. Therefore, the height to the base is CD, because it creates 90 degrees with the extended 90 degrees EO. So CD is the height to the base of this green triangle COE. So the height is CD. Over 2. So in total, we found out that the area of the green triangle COE equals to the base OE times the height to the base, that is CD, over 2. It is given us the question that OE equals to 5, so we substitute OE by 5 times CD. CD is the line segment that we are looking for this question, it is equal to X. So we substitute CD by X. Over 2. So in total, we found out that the area of the green triangle COE is equal to 5x over 2. Likewise, calculate the area of this right triangle OEN. What is the area of this right triangle OEN? Actually, the area of this right triangle COE equals to 5x over 2. But we can calculate the area of this right triangle COE in a different way. We choose the base of CO, and the height to the base will be NM. Because the height to the extended base CO is NM. So the area of this entire CO equals to the base CO times the height to the base. The height to the base must create 90 degrees with the extended base CO. CO is the base. Again, the height to the base must create 90 degrees with the extended CO. The extended CO is CN. So the height to the base must create 90 degrees with the extended base. We find this point as G. So EG creates 90 degrees with the extended base CO. So we define EG as H because it is the height of the base of the green triangle COE. So the area of the green triangle COE. We calculate the area of the green triangle COE in a different way. We choose the base instead of choosing the base as OE, we choose the base as CO. So the area of triangle COE equals to the base times the height over 2. Again, we choose the base of this green triangle COE as CO. Again, the height to the base must create 90 degrees with the extended base CO. The extended base CO is CN. And EG indeed creates 90 degrees with the extended base CO. We defined EG as H, so it equals to H. The height H equals to H over 2. So total we found out that the area of this green triangle CO equals to the base CO times the height H over 2. But CO equals to 9. It is the radius of the circle equals to 9. So we substitute CO by 9 H over 2. So in total we found out that the area of the green triangle COE equals to 9H over 2 square unit in size. Likewise, we calculate the area of this triangle OEN. And again, we calculate the area of this triangle ONE. The area of triangle ONE, this triangle ONE, the area of this triangle, it is not the triangle, the area of this triangle ONE equals to the base of the triangle times the height over 2. We choose the base of this right triangle ONE as ON. the height is EG because it's create 90 degrees with the base ON. Again, the height is EG, that creates 90 degrees with the base ON. This angle equals to 90 degrees, this angle equals to 90 degrees. And EG equals to H, and it's in itself according to our definition. So the height is H. The height is H over 2. So in total, we should find out that the area of triangle ONE equals to ON times H over 2. ON is the radius of this circle, that is equals to 9. Again, ON is the radius of this circle, that is equals to 9. So we substitute ON by 9. So it is 9H over 2. So in total, we found out that the area of triangle ONE equals to 9H over 2 square units in its size. But we already found out that the area of triangle COE also equals to 9H over 2. So the area of triangle COE also equals to 9H over 2 square units in its size. And because of the fact that the areas of those two triangles are equal to each other, it means that in the area of triangle, the area of this, and she found out that the area of this right triangle COE equals to the area of this right triangle OEN. So it is now, and she found out that the area of the right triangle COE is equal to the area of the lower triangle ONE. What is the area of the big triangle CEN? What is the area of this big triangle CEN? The area of the big triangle CEN, this big triangle CEN, triangle CEN consists of those two triangles, the green triangle and triangle EON. Therefore, the area of the big triangle CEN must be equal to the areas of the two components that it consists of. This is to say it equals to the area of this green triangle COE plus the area of this lower triangle EON. So in total, we should find out that the area of this big triangle CON, the area of the big triangle CEN equals to the area of triangle COE plus the area of triangle EON. But we already found out that the area of triangle COE equals to the area of triangle ONE. Therefore, the area of the big triangle CEN equals to the area of the green triangle COE plus the area of the lower triangle EON. But because of the fact that the area of the green triangle EON or NOE doesn't matter, it equals to the area of triangle COE, we substitute the area of triangle EON by the area of triangle COE. In total, we found out that the area of triangle CEN equals to the area of triangle COE plus the area of triangle COE, that is 2 times the area of triangle COE. So the number we found out that the area of the big triangle CEN is twice as much as the area of the small green triangle COE. It is 2 times the area of the big of the green triangle COE. And again, in total, we found out that the area of this big triangle CEN, we have this big triangle CEN equals to 2 times the area of this green triangle COE. So this will be equation 1. So in the next step, we will calculate the area of this big triangle CEN. We know that the area of the big triangle CEN equals to 2 times the area of this green triangle, but we calculate the area of this big triangle CEN by using the formula that the area of any triangle equals to the base of the triangle times the height over 2. So the area of the big triangle CEN equals to the base of the triangle times the height over 2. Now this big triangle CEN equals to the base of the triangle times the height over 2. We'll choose the base of this big triangle CEN as CE. The height to the base must create 90 degrees with the base CE. The height to the base must create 90 degrees with the extended base CE. The extended base CE is CM, and MN definitely creates 90 degrees with the extended base CE, that is CM. Why? Because this is a right angle. So MN is the height to the base CE. So this creates 90 degrees with the extended base CE. This is a right angle. So MN is the height to the base over 2. In total, we found out that the area of the big triangle CEN equals to CE times MN over 2. So the area of the big triangle CEN in total is equal to the base CE. This is the base CE. From the drawing it is very easy to see that the base CE in total equals to A plus A, that is 2A. A plus A is 2A. C is 2A times the height MN. According to our definition, Mn equals to B units in its length. So substitute Mn by B. Mn is B over 2. So total we found out that the area of the big triangle CEN equals to 2AB over 2. Here we have 2 in the denominator, 2 in the denominator, so 2 will get cancelled. So this expression, 2 will get cancelled, so this expression equals to AB. So in total, we found out that the area of this big triangle CEN equals to A times B squared in size. So, okay, now the area of the big triangle CEN equals to A times B squared in size. And we already found out that the area of the green triangle COE of the green triangle COE equals to 5x over 2, and actually found out that the area of this green triangle COE is half of the area of the big triangle CEN. And again, we only found out that the area of the big triangle COE is twice as much as the area of this green triangle COE. And again, we found out that the area of the big triangle CEN is twice as much as the area of the green triangle COE. We can write here that the area of this green triangle COE is half of the area of this the green triangle CEN. So if we divide this equation by 2, equation 1 by 2, we get that the area of this green triangle COE equals equals to the area of the big triangle CN over 2. You just divide this equation 1 by 2. So the area of the great triangle COE equals to the area of the big triangle CN over 2. But the area of the big triangle CN equals to AB. So we can write here that the area of the big triangle CN equals to AB over 2. So total we found out that the area of the green triangle COE equals to AB over 2. And again, in total we found out that the area of this green triangle COE equals to AB over 2 square units in size. In the next step, we will implement rule 65 in our domain. Repeat again, we will implement rule 65 in our domain. Repeat quickly on rule 65. According to rule 65 is true in any circle. This is the circle that could be any circle. If chord AB intersects with chord CD at point O, then AO times OB equals to CO times OD. In the domain we have a circle. This is chord AB that intersects with this chord CD at point O. This moment the following equation is to AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. So we can definitely implement rule 65 in our domain. Because in our domain, this is called AB, the big chord AB. It's actually the diameter of the circle. Chord AB intersects with chord AB intersects with chord CM is point E. Chord CM is point E. The intersection point between chord AB and chord CM occurs at point E. So we have all the requirements of rule 65 are satisfied, and therefore we can implement rule 65 in our domain. According to rule 65, the following equation is true. AE times AB equals to CE times EM. And again, according to rule 65, the following equation is true in our drawing. Because of the fact that chord AB intersects with chord CE at point E, the following equation is true. AE times EB equals to CE times EM. AE equals to AO, that is 9, that is the radius of the circle, plus 5. Again, AE in total equals to AO plus OE. AO equals to 9, that is the radius of the circle, plus OE, that is equals to 5 according to what is given in the question. So, AE equals to 9 plus 5. Plus EB. EB equals to 4 units in itself according to what is given as a question. EB equals to 4 units in itself. Is equals to CE. CE equals to A plus A, that is 2A. And C equals to CQ, that is A, plus QE, that is also A. So that C equals to 2 units in itself. So we substitute CE by 2A times EM. EM equals to units in itself according to our definition. So in total we found out that 9 plus 5 is 14. 14 times 4 equals to 2AB. 14 times 4 is 56. So 56 equals to 2AB. Here we divide this equation by 2 and finally get that AB equals to 56 over 2 is 28. AB equals to 28. AB equals to 28, but we already found out that according to equation 1, the area of the green triangle CO equals to AB over 2. So write it down. We already found out that according to equation 1, the area of the green triangle COE, this is the green triangle COE, is equal to AB over 2. But we just found out that AB equals to 28. So substitute AB in this equation 1 by 28 over 2. 28 over 2 is 14. In total, we found out that the area of the green triangle COE equals to 14 square units in its size. In the next step, we calculate the area the area of this green triangle COE according to the formula that says that the area of any triangle equals to the base of the triangle times the height over 2. So the area of the green triangle COE is equal to the base of the triangle times the height over 2. We choose the base of this green triangle COE as choose the base of this green triangle COE as OE. The base is OE. So the base of this green triangle COE, we choose the base of this green triangle COE is CE. CE is the base of this green triangle COE. And the height to the base must greater than the extended base CE. the extended BCE is CM, and therefore the height to the base the extended side CE is B over 2. So we should find out that the area of the rectangle EOC equals to the base CE times the height B over 2. CE equals to A plus 8, it is 2A. We substitute CE by 2A times B over 2. We have 2 in the numerator, 2 in the denominator, so we should find out that in total the area of the rectangle COE equals to we already found out that the area of the rectangle COE equals to 14. The area of this rectangle COE equals to the base of the triangle times the height over 2. So copy the right triangle, copy the right triangle COE. Actually, we choose the base of this right triangle COE, SOE. Okay, so the area of the right triangle COE equals to the base of the triangle times the height over 2. So the area of the rectangle COE equals to the base of the triangle times the height over 2. Choose the base of this rectangle COE, SOE. And the height to the base must create 90 degrees with the extended base. Again, the height to the base must create 90 degrees with the extended base. The extended base of EO is OED. Again, the extended base of EO is ED. And CD definitely creates 90 degrees with the base, the extended base ED. This is the right angle. So the height is CD. And it's CD over 2. So in total we found out that the area of the rectangle COE equals to the base OE, that is 5 according to what is given in the question, times the height CD. CD equals to x, that is the line segment that we are looking for in this question, so instead of CD by x over 2. In total, we found out that the area of the green triangle COE equals to 5x over 2. And again, in total, we found out that the area of this green triangle COE equals to 5x over 2 square units in size. But we already found out that the area of the green triangle COE equals to 14 square units in size. So we can find out that the area of the triangle COE equals to 14 square units in size. And from this equation, we will derive that 5x over 2 equals to 14. this equation, we have that 5x over 2 equals to 14. Here we multiply this equation by 2, and finally get that 5x equals to 2 times 14 is 28. Here we divide this equation by 5, and finally get that x, this is line 7 that's wrong before this equation, is equals to 28 over 5 units in its length. 28 over 5 is 5.6 units in its length. So if you found out that the length of this line segment CD is equals to x, the length of line segment CD is equals to x, it is equals to either 28 over 5 units in its length, or in terms of numbers, is equals to 5.6 units in its length. And again, we found out that the length of this line segment CD equals to x, equals to either 28 over 5 units in its length, or in terms of numbers, the length of this line segment CD is equals to x, is equal to 5.6 units in its length. So we finished with the second question. The next step of summarize the lecture. We start with the first question, of course. In the first question, our test specified out the size of this angle APC is equals to x. So we have to find out the value of angle x. So in the domain we have, this is angle ABC. This is angle ABC is equals to 15 degrees in size. This is angle ACB is equals to 30 degrees in size. We also know that BP equals to PC. Again, our test is to find out the value of this angle x, this angle APC. So, in the first step, because of the fact that BP equals to PC, we define the length of BP as 8, therefore PC must be also equal to 8 because they are equal to each other according to what is given as the question. The next step, we extended side CA by side 9, and then we constructed angle of 15 degrees with one leg of the angle is BA, and the second leg gets 15 degrees with the leg BA. So this angle equals to 15 degrees in size according to our construction. We just constructed angle of 15 degrees with the leg BA, and then we extended this leg by side line until it touches the extended side CA. We define the touching point of the extended leg with the extended side CA. This point is point M. By doing this construction, we created triangle BMC. Triangle BMC is an associated triangle because of the fact that those triangles are both equal to 30 degrees in their sizes. Therefore, BC is the base of this associated triangle, triangle BMC. So here we can implement rule 20 in our drawing in the associated triangle, triangle BMC. According to rule 20, the perpendicular to the base of an associated triangle bisects the base. Repeat again, according to rule 20, the perpendicular to the base of an associated triangle bisects the base. In the drawing we have the associated triangle, triangle ABC. BC is the base of this triangle ABC. The perpendicular AD to the base BC bisects the base BC. That is to say, it divides the base BC into two halves. The first half is BD, this is of course equal to the second half BC, and each of us is equal to BC over 2 because BC is bisected by the perpendicular AD. So BD equals to DC equals to BC over 2. We can actually implement rule 20 in our drawing. We have the associated triangle, triangle BMC. The base is BC, so the perpendicular from point M must touch the base BC at point P. Why? Because at point P, the base BC has been bisected. The first half is BP, and the second half is PC. Therefore, the perpendicular from point M to the base BC must touch the base BC at point P, and not in any other point. So this angle equals to 90 degrees, this angle equals to 90 degrees according to construction, because MP is perpendicular to BC. This is triangle BMP. This is right triangle BMP. This right triangle BMP sin of 30 degrees equals to MP over MB. And again, this right triangle BMP sin of 30 degrees equals to MP over MB. We define the length of the opposite MB as 2B. Therefore, MB equals to 2B. So total we found out that sin of 30 degrees equals to MP over 2B. Sin of 30 degrees is 1 half, so 1 half equals to MP over 2B. So if we multiply this equation by 2B, and find out that MP equals to 2B over 2, we have 2 both sides of, and the numerator and the denominator, so 2 will get cancelled, and find out that MP equals to B units in itself. That is to say, the perpendicular MP equals to B units in itself. So this is the big triangle BMC. The big triangle BMC, AB is the angle bisector of angle MBC. That is to say, AB bisects angle MBC into two halves. Each half equals to 15 degrees in size. And again, we should know that AB is angle bisector in triangle BMC. AB bisects angle MBC into two halves. Each half equals to 15 degrees in size. AB bisects angle MBC into two halves. Each half equals to 15 degrees in size. And therefore, can you implement here the angle bisector theorem. According to angle bisector theorem, it is rule 19. This is triangle ABC. We know that AD, the red line AD, is the angle bisector of triangle ABC. That is to say, it bisects this angle BAC into two halves. Each half equals to theta. And whenever we know that we have angle bisector that bisect angle in the triangle, then because of the fact that angle bisector DA bisect angle BAC, the following relationship exists between the size of triangle ABC. BD over DC equals to BA over AC. Again, BD over DC equals to BA over CA. So actually, angle bisector theorem has two directions. The first direction says that if you know that AD is the angle bisector of triangle ABC, then angle bisector AD divides the sides of this triangle ABC proportionally. That is to say, BD over DC equals to BA over AC. The converse theorem of angle bisector theorem is rule 21. If we know that line segment AD divides the sides of triangle ABC proportionally, that is to say, we know that BD over DC equals to BA over AC, then line segment AD must be angle bisector of triangle ABC. Okay. And again, angle bisector theorem has two directions. This is the second direction. The first direction is rule 19 that says that if AD is angle bisector of triangle ABC, then AD divides the sides of this triangle ABC proportionally. That is to say, BD over DC equals to BA over AC. So we can definitely implement rule 19 in our drawing. So as I mentioned before, in the big triangle BMC, AB is the angle bisector of triangle MBC. Therefore, angle bisector AB divides the big triangle MBC proportionally. That is to say, MB over BC equals to MA over AC. Again, because of the fact that AB is the angle bisector of the big triangle MBC, angle bisector AB divides the sides of this triangle MBC proportionally. That is to say, MB over BC equals to MA over AC. And again, coming to rule 19, MB over BC equals to AM over AC. MB is 2B, BC is A plus A, this is 2A. MB is 2B, BC is 2A, equals to MA over AC. We have two denominators, so 2 will get cancelled, and finally found out that B over A equals to MA over AC. B over A equals to MA over AC. So this is the right triangle MPC. In the right triangle MPC, line segment AP divides the sides of this right triangle MPC proportionally. That is to say, B over A equals to MA over AC. And because of the fact that line segment AP divides the sides of this right triangle MPC proportionally, it means that line segment AP must be the angle bisector of the right triangle MPC. This is the opposite rule of rule 19, the converse rule of rule 19. In the right triangle MPC, line segment AP divides the sides of triangle MPC proportionally. That is to say, B over A equals to MA over AC. And therefore, line segment AP must be the angle bisector of triangle MPC according to rule 21. AP is the angle bisector of triangle MPC according to rule 21. And because of the fact that MB AP is the angle bisector of the right triangle MPC, it means that angle bisector AP bisects angle MPC into two halves. And again, AP is the angle bisector of triangle MPC, and therefore AP bisects angle MPC into two halves. And because of the fact that angle MPC is a right angle, each half must be equal to 45 degrees inside. So the first half MPA equals to 45 degrees, and the second half APC, this is angle X, that is the angle that we are looking for this equation, must be also equal to 45 degrees in size. So if we found out that angle bisector AP divides angle MPC, angle by sub to AP divides angle MPC into 2 halves. But angle MPC is the right angle, therefore each half must be equal to 45 degrees in its size. The first half MPC is 45 degrees, and the second half APC, angle APC, is angle X, that is the angle that we are looking for this question, is equal to 45 degrees in its size. So if you found out that the angle that we are looking for this question, that is angle APC, is equal to angle X, is equal to 45 degrees in its size. So we finish to repeat on the first question, and the second, and the next step, repeat on the solution of the second question. In the second question, our task is to find out the length of this line segment CD is equal to X. So we have to find out the value of line segment X is equal to CD. So in the drawing we have a semicircle. We know that CQ equals to PQ equals to QE, and this is a right angle, this is also a right angle. We also know that line segment QE equals to 5 units in itself. This is line segment EV, this is equals to 4 units in itself. And again, our task is to find out the length of this line segment CD is equal to X. We have to find out the value of this line segment X is equal to CD. So first of all, we join points C and P together by a straight line. By joining points C and P, we get the right angle CPQ. The right angle CPQ, in front of those two equal sides, we have those two angles that must be also equal to each other in their sizes. So if you define the size of this angle as alpha, then the size of this angle must be also equal to alpha according to the rule that I mentioned. So in the right angle CPQ, the sum of the angles must be equal to 180 degrees. This is to say 2 alpha plus 10 degrees equals to 180 degrees. And again, right angle CPQ, 2 alpha plus 10 degrees equals to 180 degrees. According to the rule, the state that the sum of the angles in any triangle is equal to 180 degrees. Here we subtract the 90 degrees from this equation. If I found out that 2 alpha equals to 180 degrees, 180 degrees, this is 90 degrees. Here we divide this equation by 2. If I found out that the missing angle alpha equals to 45 degrees in size. So those two angles, each of them is equal to 45 degrees in size. In the next step, we joined points P and E together by a straight line. By joining points P and E, we get this triangle PQE. In triangle PQE, in front of those two equal sides, we have those two angles that must be also equal to each other in their sizes. And we also found out that the missing angles here, each of them is equal to 45 degrees in its size. So not repeat on the same process that we have already done here. So those two angles must be also equal to 45 degrees in their sizes, each of them equals to 45 degrees in its size. So in the next step, actually, in this, we know that YPQE is a right triangle because of the fact that CE is a straight line. So if we focus on the upper side of the straight line CE at point Q, here the sum of the angles must be equal to 180 degrees according to all three. All three state that the sum of the angles from one side of the straight line is equal to 180 degrees. So which angles we have the upper side of the straight line CQ at point Q, we have this angle, the right angle, plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to all three. Therefore, this missing angle must be equal to 90 degrees in its size. So after we join points P and E together by straight line, we get the right angle PQE. The right angle PQE in form of those two equal sides, we have those two angles also equal to each other in their sizes. And we already found out that those two angles are both equal to 45 degrees in their sizes, therefore those two angles must be also equal to 45 degrees in their sizes. In the next step, we completed the semicircle to a circle. So this is the circle, and then we extended side CE by straight line until it touches the circle. At this point, we find the touching point of the extended side CE with this circle. This point is point M. Likewise, we extended side CO by straight line until it touches the circle. We find the touching point of the extended side CO with this circle. With the circle, this point is point N. In the next step, we join points C and N together by straight line, and we join points B and N together by straight line. This is angle CPN, that equals to 45 degrees plus 45 degrees, it is 90 degrees, so it is a right angle. Angle CPN is a right angle. Peripheral angle CPN subtend on chord CN. Peripheral angle CPN, that is a right angle, subtend on chord CN. And according to all 7, any peripheral angle this was 90 degrees inside must subtend on the diameter of the circle. Repeat again. According to all 5, any peripheral angle this was 90 degrees inside must subtend on the diameter of the circle. Here peripheral angle MAN is the right angle, therefore peripheral angle MAN must subtend on the diameter of the circle. MN is the diameter of the circle. You can see that indeed peripheral angle MAN subtend on the diameter of the circle, that is MN. So according to all 5, because of the fact that peripheral angle CPN equals to 90 degrees in size, it must subtend on the diameter of the circle. Peripheral angle CPN subtend on CN, upon CN, and therefore CN must be the diameter of the circle according to all 5. Likewise, we have here peripheral angle CMN that subtend on the diameter of the circle. Therefore, it is the converse rule of rule 5. And because of the fact that this is peripheral angle CBN that is subtend on the diameter of the circle, CN, peripheral angle CMN must be equal to 90 degrees in size according to rule 7. So repeat quickly rule 7. According to rule 7, if a peripheral angle is subtend on the diameter of the circle, then it is equal to 90 degrees in its size. This is peripheral angle ACB, this is subtend on AB, that is the diameter of this circle, and therefore peripheral angle ACM must be equal to 90 degrees in its size, according to this rule or 5. We have only implemented all 5 in our drawing, because in our drawing we have peripheral angle CBM, that is subtend on CN, that is the diameter of this circle, and therefore peripheral angle CBN must be equal to 90 degrees in its size, according to rule 7. Those two angles are defined as vertex angles, and we know that vertex angles are equal to each other. But this angle equals to 45 degrees, therefore this angle must be also equal to 45 degrees in its size, according to the rule that vertex angles are equal to each other. So in this one triangle EMN, this angle equals to 45 degrees, this angle equals to 90 degrees, and therefore this first missing angle must be equal to 45 degrees in size, according to the rule that says that the sum of the angles in any triangle is equal to 180 degrees. Okay. So in the next step, we implemented all 56 in our drawing. According to all 56, all 56 is drawn in any circle, so in any circle if chord AB intersects with chord CB at point O, then the following equation is to AO times OB equals to CO times OD. So again we have chord AB that intersects with chord CD at point O. This drawing, the following equation is to AO times OB equals to CO times OD. Again AO times OB equals to CO times OD. In our drawing, we have chord AB that intersects with chord CE chord CM at point E. Again, we have chord AB that intersects with chord CM at point E. Therefore, according to all 56, the following equation is true. AE times EM equals to CE times E. AE times EB equals to CE times EM. And again, according to all 56, we know that chord AB intersects with chord CM at point E, and therefore according to all 56, the following equation is true. AE times EB equals to CE times EM. AE equals to 9 plus 5, that is 14, times EB equals to 4. So in total, we have here A is 9 plus 5 times BE, that is 4, is equals to CE times EM. CE is A plus A, that is 2A, and EM is B. And again, C equals to 2A and EM equals to B. So in total, we found out that 9 plus 5 times 4 equals to 2A times B. 9 plus 5 is 14, and 14 times 4 equals to 2AB. 14 times 4 is 65, so 65 equals to 2AB. Here we divided the equation by 2 and finally found out that AB equals to 56 over 2, that is 28. So AB equals to 28 units in its length. The next step, we calculated the area of this main triangle COE. The area of this main triangle COE equals to the base of the triangle times the height over 2. We choose the base as CO. CO is the radius of the circle equal to 9 times the height. The height to the extended base CO is H. over 2. So in total we found out that the area of the green triangle COB equals to 9 times the height edge over 2. The area of the green triangle COE equals to 9 edge over 2 square root in size. Likewise, we calculated the area of this green triangle, the area of this triangle OEN. The area of this triangle OEN equals to the base ON, that is 9, because it is the radius of the circle, that is 9, times the height edge over 2. So in total, the area of this triangle OEN equals to 9 edge over 2, exactly like the area of this triangle OEN, that also equals to 9 edge over 2. So the area of those two triangles are equal to each other, and the area of the big triangle CEN equals to the sum of the areas of those two triangles that it consists of. So the area of the big triangle CEN equals to the area of this green triangle COE plus the area of this triangle OEN. And because of the fact that the area of the green triangle COE equals to the area of triangle OE, it means that the area of the big triangle CEN equals to the area of the green triangle COE, and we substitute the area of this triangle OEN plus the area of this green triangle COE. So the area of the big triangle CEN equals to 2 times the area of this green triangle COE. So we found out that the area of the big triangle CEN is twice as much as the area of this green triangle COE. Okay. Of the area of this green triangle COE equals to the area of the big triangle CEN over 2. This is the half of the area of the big triangle CEN. And you can calculate the area of this green triangle COE according to the formula that the area of any triangle equals to the base of the triangle times the height over 2. So the area of this green triangle COE equals to the base, that is CO times the height edge over 2 the area of the green triangle COE equals to the base of the triangle times the height over 2. We choose the base as CE, the base of this green triangle COE is CE, and the height to the base must rate 90 degrees with the base. The height to the base must rate 90 degrees with the extended base CE. The extended base CE is CM, and MN rates 90 degrees with the extended base CM, because this is a right angle. So in total, the area of this triangle CEO equals to the base CE times the height MN over 2. And again, the area of the green triangle CEO equals to the base CE times the height B over 2, because MN equals to B, so MN by B. So it is the area of the green triangle CO equals to the base CE times the height B over 2. CE equals to A plus 8, it is 2A. So we substitute CA by 2A, and found out that the area of the green triangle CO equals to 2AB over 2. We have 2 in the numerator and 2 in the denominator, so in total we found out that the area of the green triangle CO equals to actually we know that the area of the big triangle CEN is twice as much as the area of this green triangle CEO. So actually calculated the area of this big triangle CEN. The area of this big triangle CEN equals to the base CE, that is 2A, times the height over 2. and we choose the base of this big triangle CEN as MN. Actually, the height of the big triangle CN must create 90 degrees with the extended base CE. The extended base CE is CM. So the height to the base is MN. So in total we found out that the area of the big triangle CEN equals to the base CE, that is 2A, plus the height times the height MN, that is B over 2. So in total the area of the big triangle CEN equals to 2A times B over 2. So it is 2AB over 2 is AB. So total we found out that the area of this big triangle CEN equals to A times B. Okay, the area of this big triangle CEN equals to A times B squared in its size. And we already found out that the area of the great triangle COE is half of the area of the big triangle CEN. But we just found out that the area of the big triangle CEN equals to AB. Therefore, the area of the great triangle COE equals to AB over 2. It is half the area of the big triangle CEN. So it is AB over 2. Now we implement rule 56 in our drawing. We only found out that according to rule 56, A times B equals to 28. According to rule 56, A times B equals to 28. So we substitute AB by 28. In total, we found out that the area of the great triangle CO equals to 28 over 2 is 14. The area of this great triangle COE equals to 14 squared in its size. In the next step, we calculated the area of this great triangle COE, using the formula that says that the area of the triangle equals to the base of the triangle times the height over 2. So we choose the base of this triangle COE as OE, and the height to the base must create 90 degrees with the extended base. Again, the height to the base must create 90 degrees with the extended base. The base is OE, the extended base is EO. The extended base is EO. So the height to the base must create 90 degrees with the extended base EO. CD creates 90 degrees with the extended base EO. So in total, the area of the great triangle CO equals to the base OE times the height MN times the height OE, that is equals to X over 2. Repeat again, the area of this great triangle EO equals to the base EO times the height CD over 2. So we know that again the area of the great triangle CO equals to the base OE, that is 5, times the height CD, that is X over 2. So in total the area of the great triangle COD equals to 5x over 2. Repeat again, in total the area of this great triangle COD equals to 5x over 2. The area of the great triangle COD equals to 5x over 2. But we already found out that the area of the great triangle COD equals to 14. The area of the great triangle equals to 14. So we can write down that the area of the great triangle COD equals to 14. So those two sides of the equation are equal to each other. That is to say, 5x over 2 equals to 14. If we multiply this equation by 2, we found out that 5x equals to 28. Here we divided this equation by 5 and found out that x equals to 28 over 5 units in itself. In terms of numbers, 28 over 5 is 5.6 units in itself. So we found out that the length of this line segment CD is equal to x. It is equal to either 28 over 5 units in itself. In terms of numbers, it is equal to 5.6 units in itself. Okay, thank you very much.